This solar system can power an entire business, store massive energy, and almost eliminate electricity bills without exporting a single watt back to the grid. Most people get this type of system wrong, and that one mistake can cost thousands or even shut the system down completely. Today, I'll show you how to do it the right way. This is a 40 kilowatt 3-phase Dye hybrid solar system, and this video was requested by one of you. Whether you're a beginner, an installer, or a business owner planning a serious solar setup, this guide will save you time, money, and stress. Here's what we're working with. A 40 kilowatt 3-phase Dye hybrid solar inverter. This is the brain of the system. 60 kilowatt hours of high voltage batteries, giving you power day and night, and 70 bifacial solar panels, each rated at 600 watts, giving a total of 42 kilowatts of solar generation. And here's the most important part: zero grid export. That means no power is sent back to the utility, which is required in many countries. Later in this video, I'll show you exactly how to configure this correctly. By the end of this video, you'll understand how to plan the system, connect everything safely, and avoid the most common beginner mistakes without confusing technical language. Before we go any further, a quick but important warning. This is a high-voltage 3-phase electrical system. If you are not trained or licensed, do not attempt this installation yourself. This video is for educational purposes only. Safety always comes first. If this is already helpful, hit the like button. It really helps the channel and lets me know you want more content like this. Now let's start where every successful solar project begins: planning before installation. The first step is site assessment, and this is where many beginners make mistakes. Your roof must support 70 solar panels, which is roughly 2,100 kilograms. Always confirm this with a structural engineer. You'll also need approximately 180 square meters of unshaded roof area. Even small shadows can seriously reduce system performance, so check the roof at different times of the day. Next, confirm that 3-phase power is available and measure the distance from the roof to the inverter location. After that, permits and approvals. Contact your utility company early and clearly declare zero grid export. Always get written approval. Check local building permit requirements. This process can take weeks, so don't delay it. A licensed electrician is usually required for approvals and insurance. Now let's talk about tools and materials. You don't need fancy equipment, just the right tools. Basic drills, a torque wrench, proper crimping tools, a multimeter, correct cable sizes, protection breakers, and grounding equipment. Finally, safety equipment. Always wear insulated gloves and safety glasses. Use proper fall protection when working on roofs. Have a voltage tester and a Class C fire extinguisher nearby, and never work alone. With planning complete, we can now move on to the component overview, starting with the inverter. Now let's take a closer look at the main components of this 40 kilowatt hybrid solar power system. At the center of the system is the Deye 40 kilowatt 3-phase high voltage hybrid inverter. This inverter is responsible for managing power from the solar panels, the battery system, the utility grid, and the electrical loads. It features 4 independent MPPTs, allowing multiple solar strings to be connected while maintaining high efficiency and flexible system design. The inverter delivers 40 kilowatts of 3-phase AC power and supports both grid-connected and backup operation. Because this project requires zero export, the inverter will be configured so that no excess solar power is fed back into the utility grid. The Deye inverter also supports high-voltage lithium batteries, generator input, remote monitoring, and advanced protection features, making it suitable for commercial installations. Energy storage is provided by a 60 kilowatt-hour high-voltage lithium battery system. This battery operates in a voltage range between 160 and 800 volts, which allows lower current, higher efficiency, and reduced cable losses compared to low-voltage batteries. The battery system includes an integrated battery management system, or BMS, which communicates directly with the inverter to control charging, discharging, and safety protections. Stored energy can be used during power outages or periods of high consumption, increasing energy independence and reliability. Solar generation comes from JA Solar 600-watt N-type bifacial panels. These high-efficiency modules produce power from both the front and rear sides of the panel, increasing total energy yield when installed over reflective surfaces. Each panel has an efficiency of 22.7% with a maximum power voltage of 43.76 volts and a maximum power current of 13.71 amps. In total, 70 panels are installed, providing a combined solar capacity of 42 kilowatts. In addition to the main equipment, several supporting components are required to safely complete the installation. On the DC side, solar DC cables and MC4 connectors are used to connect the panels to the inverter. These cables are rated for high voltage, ultraviolet exposure, and outdoor conditions. On the AC side, 3-phase AC cables connect the inverter to the main distribution board and the utility grid. Proper cable sizing is critical for handling the full system load safely. Circuit breakers and disconnect switches are installed on both the DC and AC sides to protect the system and allow safe maintenance. This includes DC isolators for the solar array, battery breakers, and AC protection devices. Mounting hardware such as rails, clamps, inverter brackets, and battery racks ensures that all components are securely installed and properly supported. Finally, grounding and earthing equipment is installed to protect the system from electrical faults and lightning. All panels, inverter, battery systems, and metal structures are bonded to a common grounding system. With all system components clearly identified, we can now move on to the installation process, starting with mounting and wiring the solar panels. Before installing the solar panels, we must first finalize the string sizing and DC electrical design. This step ensures the system operates safely, efficiently, and within the inverter's voltage and current limits. This system uses 70 JA Solar 600-watt N-type bifacial panels, giving a total solar capacity of 42 kilowatts. Each panel has a maximum power voltage of 43.76 volts and an open circuit voltage of 52.4 volts. The Deye 40-kilowatt hybrid inverter has a maximum DC voltage of 1,000 volts and an MPPT operating range between 150 and 850 volts. Each MPPT can accept up to 36 amps with a short circuit current limit of 55 amps. Solar panel voltage increases in cold weather, so we must apply a cold temperature correction to the panel's open circuit voltage. For N-type modules, we use a temperature coefficient of approximately minus 0.25% per degree Celsius. Using a conservative minimum temperature of minus 10 degrees Celsius, the corrected open circuit voltage increases to approximately 57 volts per panel. Based on this corrected voltage, the maximum safe number of panels per string is 17. 18 panels would exceed the inverter's 1,000-volt limit and must not be used. For best performance and voltage margin, we select 14 panels per string. This produces an operating voltage of approximately 612 volts, which is ideal for the Deye inverter's MPPT range. The 70 panels are divided into 5 identical strings, each containing 14 modules. This results in a total DC capacity of 42 kilowatts with perfectly balanced strings. 2 strings are connected to each MPPT input, keeping the operating current at approximately 27 amps, which is well below the inverter's maximum limit. For commercial installations, a DC combiner box is recommended for protection and maintenance. Each combiner includes string fuses, DC surge protection, and a DC isolator switch. With the string sizing verified and designed for cold temperature conditions, we can now move on to the physical installation of the solar panels. Section 4. DC side electrical connections. Panel strings to DC combiner box to 40 kilowatt hybrid inverter. Now we'll connect the DC side of the solar system step by step, starting from the panels and ending at the inverter. We are using 70 600-watt solar panels. These are divided into 5 strings, with 14 panels connected in series in each string. Let's start with the first string. Place 14 panels in a line. Connect the positive terminal of the first panel to the negative terminal of the second panel. Then connect the positive of the second panel to the negative of the third panel. Continue this same pattern until all 14 panels are connected in series. When the string is complete, you will have one free negative cable at the first panel and one free positive cable at the last panel. This is one complete solar string. With 14 panels in series, the string voltage stays safely below the inverter's 1000-volt DC limit, even in cold weather, and the current remains the same as a single panel. Repeat this exact process to create all 5 identical strings. Each string must be wired the same way, with the same number of panels and the same orientation. Now we connect the strings to the DC combiner box. Bring the positive and negative cables of each string into the combiner box using proper DC solar cable and glands. Keep each string separated and clearly labeled. For each string, connect the positive cable first to its own DC fuse. We use a 20-amp GPV DC fuse rated for 1000 volts. This fuse protects the string and prevents reverse current from other strings. From the output of the fuse, connect the cable to the positive bus bar inside the combiner box. Next, connect the negative cable of the same string directly to the negative bus bar. Only the positive side is fused. Repeat this same connection process for all 5 strings, one by one. Once all string fuses are connected, install the DC surge protection device inside the combiner box. The DC SPD is rated for 1000 volts and protects the inverter from lightning and voltage surges. Connect the SPD positive terminal to the positive bus bar, the negative terminal to the negative bus bar, and the earth terminal to the grounding bar. Make sure the grounding cable is short and securely connected. After the SPD, we install the DC isolator. This is a 2-pole DC isolator rated for at least 1000 volts and 40 amps. The isolator allows safe shutdown during maintenance or emergencies. Connect the positive and negative outputs from the combiner bus bars to the input of the DC isolator. Then connect the isolator output cables to the inverter DC inputs. Now we connect the strings to the MPPTs. This 40 kilowatt hybrid inverter has 4 MPPTs, and each MPPT can accept 2 strings. We are using 5 strings total. Connect string 1 and string 2 to MPPT 1 using the 2 available DC input ports. Connect string 3 and string 4 to MPPT 2. Connect string 5 to MPPT 3. MPPT 4 will remain unused. Make sure each string's positive and negative cables are connected to the correct MPPT terminals and that polarity is correct. Never mix strings from different MPPTs. Before turning anything on, confirm that all DC isolators are switched off, all fuses are installed, all connections are tight, and grounding is complete. This completes the DC side electrical connections from the solar panels to the inverter. Step 5. Battery to inverter connection. Now we'll connect the high-voltage lithium battery system to the inverter. This step is critical, so take your time and follow the sequence exactly. This system uses a 60 kilowatt-hour high-voltage lithium battery with a nominal voltage range from 160 volts up to 800 volts. Because this is high voltage, incorrect connections can be extremely dangerous. Before starting, make sure the inverter is completely powered off, the DC isolator is off, and all battery breakers are in the off position. High-voltage batteries are always installed in series inside the battery rack by the manufacturer. You should never change the internal battery configuration. Your job is only to connect the battery output terminals to the inverter. The battery system includes built-in protection through the BMS, or Battery Management System. The BMS protects against overvoltage, undervoltage, overcurrent, short circuit, and temperature faults. Even with this protection, safe wiring is still essential. We always connect the battery system in this order: grounding first, power cable second, and communication cable last. Start with grounding. Connect the battery grounding terminal to the main grounding bar using a copper earth cable. This grounding cable must be properly sized and securely tightened. Grounding is mandatory for safety and for correct BMS operation. Next, we connect the battery power cables. The battery has a high voltage positive terminal and a high voltage negative terminal. Use only manufacturer approved high voltage DC cables. These cables must be rated for at least 1000 volts DC and suitable for lithium battery system. For a 60 kilowatt-hour high voltage battery, the recommended cable size is typically 35 square millimeters to 50 square millimeters copper, depending on inverter requirements and cable length. The insulation must be double-layered and clearly marked for DC. With the battery breaker still off, connect the positive battery cable to the inverter's battery positive terminal. Then, connect the negative battery cable to the inverter's battery negative terminal. Tighten all terminals using a torque wrench according to the manufacturer's specifications. Loose connections can cause heat, voltage drop, and failure. After the power cables are connected, we connect the communication cable. The communication cable links the battery BMS to the inverter, usually using a CAN or RS-485 connection. This cable allows the inverter to read battery voltage, current, state of charge, and protection status. Plug the communication cable into the battery communication port and the corresponding port on the inverter. Make sure the connection is firm and the correct protocol is selected later in the inverter settings. Do not turn on the battery before the communication cable is connected. Without communication, the inverter cannot properly control charging and discharging. Once grounding, power cables, and communication are complete, double-check everything. Confirm correct polarity, tight connections, proper cable routing, and secure grounding. Only after all checks are complete should you turn on the battery breaker. The battery will power up and the inverter will detect the battery through the BMS. This completes the battery to inverter electrical connection.
Step 6. AC side connections, grid and loads. Now we move to the AC side connections, starting from the grid and ending at the building loads. This system uses a three-phase supply, which includes L1, L2, L3, neutral, and ground. Before making any connections, ensure the grid supply is completely switched off and locked out for safety. We begin with the energy meter connection. The three-phase energy meter is installed on the main incoming grid supply before the inverter. Its purpose is to measure grid power flow accurately, so the inverter can control zero export. Connect grid phase L1, L2, and L3 from the utility supply to the corresponding input terminals of the energy meter. Connect the neutral wire to the meter's neutral terminal and the ground wire to the grounding bar. From the output side of the meter, run the same L1, L2, L3, neutral, and ground cables toward the inverter protection devices. Next is the AC isolator. The AC isolator allows you to safely disconnect the inverter from the grid for maintenance or emergencies. Use a three-phase AC isolator rated for at least 400 volts AC and a current rating suitable for the inverter, typically 63 to 100 amps. The isolator must disconnect all three phases and neutral. Connect the meter output to the AC isolator input, matching L1, L2, L3, and neutral. The isolator output will feed the next protection device. After the isolator, install the undervoltage and overvoltage protection relay. This relay protects the inverter from unstable grid conditions. It monitors grid voltage and disconnects the system if the voltage goes outside safe limits. Connect the isolator output to the input of the voltage protection relay. Then connect the relay output onward to the surge protection and breakers. Make sure the relay is configured according to local grid regulations. Next, install the surge protection device on the AC side. Use a Type 2 AC surge protection device rated for three-phase 4-wire systems. The SPD protects the inverter from lightning and switching surges. Connect each phase and neutral from the line to the SPD terminals, and connect the SPD earth terminal directly to the grounding bar using a short, thick grounding conductor. Proper grounding is essential for the SPD to work correctly. Now we install the AC MCB for grid protection. The AC MCB protects the inverter from overcurrent and short circuits. Use a 3-phase MCB rated according to the inverter's AC input current, typically 63 amps for a 40 kilowatt 3-phase inverter. Connect the output of the surge protection device to the input of the AC MCB. From the output of the MCB, run L1, L2, L3, and neutral to the inverter's grid input terminals. Now we connect the inverter to the grid. At the inverter grid input, connect L1, L2, L3, neutral, and ground exactly as labeled. Tighten all terminals properly and confirm correct phase order. Incorrect phase sequence can cause inverter faults. Next, we connect the AC output side for the loads. The inverter AC output feeds the building loads through a separate load MCB. This breaker protects the load side and allows isolation of the building from the inverter. Use a 3-phase load MCB rated according to the load current, typically the same or slightly lower than the grid MCB rating. Connect the inverter AC output terminals to the input of the load MCB. From the output of the load MCB, connect L1, L2, L3, neutral, and ground to the main distribution board of the home or facility. All building loads will now receive power from the inverter when solar or battery energy is available, and from the grid when required. Before powering up, double-check all AC connections, confirm grounding is secure, verify correct breaker ratings, and ensure all isolators are in the off position. This completes the AC side electrical connections from the grid to the inverter and from the inverter to the building loads.
Step 7. Current Transformer or CT Clamp. Now we install the Current Transformer or CT Clamp. This component is what enables zero grid export. The CT clamp measures how much power is flowing between the grid and the building. The inverter uses this information to make sure no electricity is sent back to the utility grid. The CT must be installed on the main grid supply cable before the inverter connection and after the utility meter. This position allows the inverter to see the total power flow of the site. For a 3-phase system, use a 3-phase CT set or individual CTs for each phase, depending on the meter type. Each CT must be installed on one phase conductor only. Never place a CT around neutral or around multiple cables together. Open the CT clamp and place it around phase L1. Make sure the arrow or marking on the CT is pointing toward the grid, not toward the load. Correct direction is critical. If the CT is installed backward, the inverter will not control export correctly. Repeat the same process for phase L2 and phase L3. Ensure all CTs face the same direction and are fully closed. After installing the CT clamps, connect the CT signal cable to the energy meter or directly to the inverter depending on the system design. Match the CT inputs correctly for L1, L2, and L3. Do not extend the CT cable unless the manufacturer allows it. Secure the CT cables neatly and keep them away from high-voltage power cables to avoid interference. Once connected, the inverter will use CT measurements to continuously monitor grid power flow and automatically limit export to zero. This completes the CT installation for zero grid export control.
Step 8. Grounding and final checks. Now we complete grounding and perform final checks before powering on the system. Proper grounding is essential for safety, equipment protection, and correct operation of the inverter, batteries, and surge protection devices. Start with the main grounding system. Install a dedicated earth electrode or grounding rod according to local electrical standards. This ground point will be the reference for the entire solar system. Connect the inverter grounding terminal to the main grounding bar using a copper earth cable. The grounding cable must be properly sized, securely tightened, and free of paint or corrosion at the connection points. Next, ground the solar panel frames. All panel frames must be bonded together using grounding lugs or grounding clips and then connected to the main grounding bar. This protects against electric shock and lightning. Now, ground the DC side components. Connect the DC combiner box grounding terminal to the grounding bar. Make sure the DC surge protection device is also connected to the same grounding point with a short and thick earth conductor. After that, ground the AC side components. Connect the AC surge protection device, AC isolator enclosure, distribution boards, and any metal enclosures to the grounding bar. Next, ground the battery system. Connect the battery cabinet or rack grounding terminal directly to the grounding bar. Proper grounding is required for battery safety and correct BMS operation. Once grounding is complete, perform final electrical checks. Verify that all DC connections are tight and correctly polarized. Confirm that all DC fuses are installed and rated correctly. Make sure the DC isolator is in the off position. Check the battery connections again. Confirm correct polarity, secure terminals, communication cable connection, and battery breaker in the off position. Inspect the AC side. Confirm correct phase sequence, correct breaker ratings, secure neutral connections, and all AC isolators and MCBs in the off position. Verify the CT clamps are installed in the correct direction and securely connected. Use a multimeter to check continuity of grounding and to confirm there are no short circuits between positive and negative conductors. Make sure all cable routes are tidy, protected, and clearly labeled. Only after all checks are complete and confirmed should you proceed to system power-up and inverter configuration. This completes grounding and final safety checks. Monitoring and maintenance. In this final section, we'll cover system monitoring and routine maintenance. Proper monitoring ensures maximum performance, while regular maintenance extends the life of your solar, battery, and inverter system. The Deye hybrid inverter supports remote monitoring through its cloud-based platform. Connect the inverter using Wi-Fi, Ethernet, or a data logger. Once registered, the system provides real-time and historical performance data. Daily monitoring helps detect issues early. Key values to check include solar production, inverter output, grid power, and battery state of charge. In zero export systems, always verify that grid export remains at or near zero. For the high-voltage battery system, monitor state of charge, charge and discharge power, and alarms. The battery management system automatically protects against overvoltage, overcurrent, and temperature extremes. Any repeated alarms should be investigated immediately. Routine maintenance is simple but essential. Visually inspect DC and AC cables, breakers, and grounding connections. Check for dust, corrosion, loose terminals, or physical damage. Solar panels should be cleaned periodically to maintain efficiency, especially in dusty environments. The Deye platform allows remote firmware updates. Always perform updates during low load periods and ensure stable power supply. Event logs and fault history help diagnose performance or protection events. Follow a simple maintenance schedule. Always switch off AC and DC breakers before performing maintenance. High-voltage solar and battery systems must only be serviced by qualified personnel. With proper monitoring and maintenance, your Deye hybrid solar system will deliver reliable performance for many years. Conclusion and results. Suggestions. So, after planning, mounting, wiring, and programming, what were the final results? Let's look at the monitoring. On this sunny day, the 42 kilowatts of solar is producing peak power. The company's loads are running directly off that solar. The excess is quietly charging this 60 kilowatt-hour battery bank. And most importantly, the grid import is hovering near zero. The CT sensors and our configuration are doing their job perfectly. Zero export, maximum self-consumption. For anyone considering a system like this, remember the key takeaways. 1. Plan meticulously.
Site assessment, permits, and string design cannot be rushed. 2. Safety is absolute. HVDC and three-phase AC are no joke. Use qualified professionals. 3. Configuration is key. The hardware is just metal without the correct software setup, especially for zero export mode. This system isn't just an expense, it's a long-term investment that takes a major operational cost, energy, and brings it under control. A huge thank you again to Hamadi RD5TM for requesting this deep dive. If you found this guide helpful, please smash the like button. It genuinely helps the channel. Subscribe and hit the bell for more detailed solar, battery, and off-grid content. Got questions? Drop them in the comments below. I try to read every single one. Want the specs, tools, or components we used? All links are in the description. Thanks for watching. Until next time, keep harnessing the sun.